So now we are going to see JVM architecture. So JVM architecture consists of class loader, class loading, and memory area, and the execution engine, and garbage collection. So here first class loading. So class loading we have three types. One is bootstrap class loader, and which loads classes. Actually, basically class loading is loading class into memory. For example, we have an employee dot class, and it will be employee dot Java is converted into dot class binary format. So this is a binary code. So basically, the class loading what it will do, it will load dot class file into memory. So Bootstrap will load the core Java classes into memory. And there is next platform class loader, also called extend. Earlier we used to call extension from Java 9. It changed to platform class loader. It will uh, load platform JDK libraries like Java.SQL, Java uh, desktop logging, something like that. And next we have application class loader. Actually, this application class loader loads our employee class and Spring framework related classes and other user related classes, other user created classes. And next we have a memory area. And this memory area, and first before that, let me complete this execution engine. In the execution engine, we have an interpreter and JIT compiler. So just-in-time compiler. What this execution engine will do is it will convert this bytecode into machine code. This interpreter will execute bytecode line by line, whereas the JIT is it will, for example, interpreter execute line by line. If this is a frequently executed code, then it will move the code to hard code, and whereas this hard code will be compiled into native machine code and uh, for a faster fetch. This every time if next time if it calls, it will directly execute it more fasterly because it is already compiled and interpret. Whereas in the interpreter, it will execute the it will convert bytecode line by line to machine code. It will cache it, and next we'll look at the memory area. In memory area, we have a method area or metaspace where it contains class metadata and static variables and all will be stored here. And next we have a heap, and here where object will be created and allocated, and this will be shared across threads. And next we have a stack, and here it will show the method calls and local variables and partial results. This is a thread stack. Each thread will execute some method, right? So that will be stored here. Thread stack. And next we have a program counter. In the interpreter, we've seen it executes line by line, right? So how we will know JVM which line is next and which line we are currently executing? Through this program counter, it stores the JVM execution address instruction. It stores instruction address executed by JVM. And next we have a native method stack. This native method stack holds it supports a native method library, native method execution, and it stores, for example, system dot current time release. Basically, this is a native method. And next, garbage collector. So earlier, we from till Java 8, we have a serial GC, parallel GC, and all. In serial and parallel GC, heap will be split into two space. One is young generation and old generation. Young generation will have a Eden and survivor S0 and survivor S1. In Eden space only, new object will be created. And if you see, if new object created, where the address will be stored? The address will be stored in the stack call. So if thread create a new object, it will be created in the heap, and that address will be stored in the stack variable. For example, employee em. This employee variable stored in the stack. And we have a old generation. Uh, this garbage algorithm has a mark, sweep, and compact. So what this mark and sweep will do is, mark sweep will do is, it will mark the uh, current living objects. For example, we have A, B, C, D, E, and let's say this B and D is not used, it not referenced in the stack. So what this will JVM will do is it will mark A, C, E as live object, and this BD as eligible for garbage collection. So in the sweep phase, it will garbage collected. So now it will look like A, B, sorry, A, and we have C and E. If you see this B, D, and all fragmented. So what in the compact space will do is it will left shift A, C, E. Now we have two spaces. Why we need to fragment is so that if any new big object comes, it will store. It will be allocated for big object. If it is fragmented, we can't store much objects, right? So that is the reason. And from Java 9 and all, we have a G1 GC, that is garbage first GC, and it's a GC and all, and there are a lot of GCs available. What this G1 GC will do is we don't have a young and old generation. We have a regions. For example, each regions can have R1, R2. This R1, R2 can be Eden or uh, S0 or old and all. So we have a free space also. So now if we have a ABCD, and also if any in the Eden Garden, we have a minor GC and major GC and full GC. For example, if Eden Garden is full, then what GC will do is it will perform minor GC. It will do this GC. And if the major GC is full, then it will do major GC. In full GC, it will do both minor and major. And if any object, for example, here AC is survived in the minor GC, we have some age limit. I think for generally it's 15. If this is survives 15 cycles, then it will move to survivor, and it will move to S1. And what it will do is it will move ACE to this survivor. It won't simply move, it will actually it is copy because copy is faster. It will copy the live object and it will be deleted here. And in the GNGC, what it will do is, for example, we have a ABCDE. If similarly we will mark here same mark and speed. It will mark ACE. Now what it will do is uh, it will check each region. What is the how many percentage of the garbage collected there? 91 percentage, 80 percentage, 70 percent, something like that. So it will select most garbage collected region and it will do the garbage collection. And what it will do is it won't simply remove perform in the region. It will move the living objects into the new region. So A, C, E will be moved to this free region. So, like this, here we no need to require a compact that competition. So here that we no need to look for that compact because it is already uh, efficiently copied into this new region, right? So here we that fragment and all efficiently cancelled out. So in case if you are in the older region, for example, here ABCD is there, then it will every time it will do that compact to remove that fragmentation. So here fragmentation not possible. It will be all the objects copied moved together. So here compact not required. And in the G1 GC, the new generation GCs, pass time is very less. If you have a more pass time, then application will be down and we might feel for example, those will be very some millisecond or microsecond. But in the microsecond, millisecond, our application will be completely fast. Whereas in the G1GC, the application fast in millisecond is very less. So it will be very efficient. And one thing about this new MG is STW, stop the world. Because for those some cases, GC cases, this application completely down, right? So this new G1 G generation Gs are to avoid uh, improve to avoid this STW. And now we will look at some important concepts. For example, we have a memory area, and this memory area only JVM will be created. RAM, we'll call it as a RAM, okay? And JVM will be created. Whenever we what during build what it will do, dot class file will be created, and from that jar file will be created. When we execute the jar, our JVM in this memory area, JVM will be created. From this JVM, we have a Java thread, and this Java thread is assigned to or mapped to the OS thread. For example, each CPU core can have theoretically can have a unlimited OS threads, and each our Java thread is mapped to this OS thread. So whenever we say employee.emp, okay, and give me this emp dot get name. So what it will do is Java thread will simply say, okay, J1 thread is reading this uh, get name. But what actually doing is this Java thread, right? It will uh, map to this OS thread, and this OS thread will ask the CPU core. It won't simply ask. Actually, there is a OS scheduler. This OS scheduler will schedule the this request to CPU core. Okay, so this OS schedule will say, okay, when you're free, give me this employee.get name. So how CPU core will fetch? Because CPU core won't know JVM heap and all. It only know RAM. So what it will do is how it will be fetched by the machine code. Actually, we have this interpreter, right? So JIT and all. So we have a binary code, and it will be converted into machine code. From the machine code, it will have the address. So what it will do is from this address, it will get from that address, it will get the fetch the employee. Actually, that if you are saying heap, then those heap will be somewhere in the RAM only. It will be allocated somewhere now in the RAM only with certain address. Okay, so that machine code from the machine code, it will get the address, and the CP core will fetch the employee.getName. It won't directly go into the RAM. First, it will actually the CPU core first will check the register and L1 cache and L2 cache and finally RAM. So if employee not get name is available in the L1 cache, it will directly fetch that value from the L1 cache. And if it is not available in L1, then L2. If it is not available in L2, then it will finally go and check it in the RAM. Suppose if we are having multiple threads, okay, thread T1, T2, and both are concurrently updating this get name function. Then in that case, what it will do is first it will be updated in the L1 cache only, and each thread holds the L1 cache. Okay, because each thread will have a each CPU core has its own CPU cache, right? Because each CPU core has its own CPU L1 cache, L2 cache. So from this L1 cache and this L2 cache, this is different. Uh, so for example, thread T1 has changed to Tamil, but thread T1 still has that name as the old not updated value, right? Because it is not updated into the RAM. So what we, in this case we need to do is we need to use volatile, or we need to use a synchronized keyword. Actually, we need to use both so that uh, one thread will update that it will be in a sequence, and this volatile will be updated in the RAM. We should not simply use that volatile keyword. For example, uh, we are using that Boolean value. Okay, it will be available in that RAM, but what this updating is, it will fetch the value and update the value, right? So in somewhere it will be overridden. For example, if you are updating 500 times, for example, I have a one counter, and if I am updating 5,000 times, so it will give me result as 4,997 or 5,001, something like that. So why? Because it's not there is a gap between this. For example, what this volatile will do is it will fetch read from the RAM, and it will update, and it will write into the RAM. So if two threads are continuously updating, then there is a gap, right? So in this gap, the value is not accurate. You will face some race condition. Okay, so it won't be updated accurately. So in this case, we need to use some compare and swap variables like atomic boolean, atomic integer. And also it is recommended to use synchronized keyword, because at the time only one thread need to access. So this is the one thing I wanted to discuss.